Hello, welcome everybody to this new session of the GEOTOP-A seminar. We have the pleasure of having today with us Dmitriy Morozov. I don't know, maybe the accent goes somewhere else.
That's
you will
perfect.
tell me. And the title is on the screen, and also you will find it in the chat. Please, Dmitry, it's all
Oh,
yours.
and all right. Well, thanks a lot for the invitation and for the introduction. It's really wonderful to be here, and I appreciate the opportunity. So I will talk about this sort of these ideas between descriptive and operational. I'll explain what I mean by this topological data analysis. When I talk about topological data analysis, I'm really going to talk about persistent homology. So one particular corner of it in which I work. And it's helpful, I find it, to have some kind of a mental model. I won't go into precise definitions, but to just build up a mental model of what we're talking about. And one of the most helpful mental models is actually perhaps the oldest use of persistence before there was not only persistent homology, but even homology. And the idea comes from mountaineering. So if I ask you what is the highest mountain in the world, there is absolutely no ambiguity with this. You will all tell me that it's Mount Everest. It's 8,850 meters, and everything is great. If I ask you for the 10 highest mountains in the world, so I had to look this up on Wikipedia. Here's the list. Number 4 on this list, Mount called Lhotse, is actually the peak next to Everest. So it's 8,500 meters. But what's interesting in this view is not Lhotse, but the peak next to it. It's called Lhotse Shar. It's just shy of 8,400 meters. So it should be number 6 on the list. It's higher than Cho-Oyu, and yet it's not. And the reason that it's not is sort of gets to the heart of what persistent homology is about. And the question is, what is a mountain, I guess, is really the key question here. And the way that this is defined in mountaineering is through what's known as a prominence. And the prominence of a peak is defined to be the height of the peak over above the lowest contour line encircling it and no higher summit. So it's simply put, it's how far down you have to go before you can climb up to something higher. So the prominence of this peak is this height. The prominence of this peak is this height, because you have to climb down to the saddle before you can climb to something higher. And you can collect this information in what we call persistence diagram, and well, you can call it a prominence diagram, where in this case on the horizontal axis you will record the height value of the saddle, on the vertical axis the height value of the maximum. And so, for example, this peak translates to this point. The fact that it's close to the diagonal means that it has smaller prominence. Exactly, the distance to the diagonal is exactly the prominence. This peak corresponds to this point, and then this peak that sort of is the global maximum corresponds to this point. And so now you can right. So you can compute this persistence diagram for the elevation function on the planet. And in principle, you could do it for everything, right? Every little bump, every little wrinkle on Everest will be some point here. Or in fact, you can think of entire planet Earth as just Mount Everest with a bunch of wrinkles in it. Now, of course, it's not possible to do in practice, because literally every little bump will be here and will crash my PDF reader. So I cut it off at 2,800 meters. But now you can actually see that when you look at this list of highest mountains, Wikipedia tells you that it's the highest mountains with prominence greater than 500 meters. And so it's really, we go from the top down and we just list the points in this diagram as long as they're above this cutoff. And so we get Mount Everest, we get K2, there's our Lhotse, and Lhotse Shar is simply not prominent enough. But of course, when you have this kind of a representation, when you can tell how significant something is, you can slice and dice this information in different ways. And so, for example, you can ask not what are the highest mountains, but what are the most prominent mountains. So mountains with highest prominence, in other words, what are the points that are furthest away from the diagonal? And you get Mount Everest, which, okay, you can expect, but you can also get Aconcagua in the highest point in Americas, Denali in North America, Kilimanjaro in Africa, right? And so you're really getting highest points on the continents, because in order to climb to something higher, you have to go all the way, descend all the way down to the ocean. Okay, so that's a mental model that I think is helpful to have in mind when thinking of persistence. But maybe to recap in a nutshell, what is going on is with persistent homology, the idea is that we have a filtration of a topological space. So we have a bunch of nested spaces. We apply homology to it. We fix some field coefficients, which will be important, and we get what will the inclusions induce linear maps between homology groups, which are vector spaces in this sequence. And the persistence diagrams that I've been showing, they really when a homology class is born and when it dies in the sequence, which in the previous picture, this was, you can think of it as I was sweeping from the top down, connected components were appearing and they were merging together. So there were changes happening in H0, and that was the tracking that we were doing. You can also think of this sequence as a representation of a AN quiver, and then it decomposes into the simple summons that have this form of intervals, and those intervals are exactly sort of the left-hand point is the birth, the right-hand point is the death, and that's how you get these persistence diagrams. So the two very concrete settings, one is what I showed you so far, which is you have a function on some topological space, a scalar function. You can look at its super level sets. That will define your filtration. So as you sweep A from top down, you will include more and more and more of the domain. And as you keep track of how the changes happen in the sequence of homology groups, you will get this pairing or this decomposition, and this will give you this birth death diagram. Another setting that is also very common, that if you've heard of persistence, you most likely have heard about, because it was heavily popularized, especially in the early days. The idea is that if you have some, you can create this filtration by growing balls around the points. So I will take my space in this filtration XR to be union of balls of radius R around these points. And so I've highlighted a few of these sublevel sets, unions of balls with different colors. And now if you simply keep track of how the homology changes in the sequence of these XRs in this filtration, you will get a pairing where classes will appear, and then there will be a unique time where a class will die. And from that, we will recover this persistence diagram. So this is the one-dimensional diagram for this particular sequence. And once you've looked at them for a while, so in the same way that you could interpret the Everest and Denali on the elevation of Earth, here you can tell that the fact that there is this highly persistent point away from the diagonal, it corresponds to the fact that from afar, this thing looks like a circle, right? Because there is going to be a one-dimensional homology class born early on that won't die until this dark gray level sublevel set. So that's what this point is. And these 10 points that kind of stick out from the diagonal, each one corresponds to the little link in this chain that this point set samples. And each one of them translates to a point here. And the points on the diagonal, very close to the diagonal, we think of them as noise. So they're kind of these transient one-dimensional classes that appear and disappear. And well, if you've seen this before and you're kind of comfortable with this idea, but this is new. This is, of course, you can think of it as a special case of the right setting, where the function is simply the distance function to the point set, right? So if we take the infimum at any point x, you just compute the distance to the closest point. The sublevel set, so not super level set, but the sublevel set is going to be exactly the union of balls, and so it's exactly the same setting. Okay. So this is, okay, persistence in a nutshell is probably the right title for this. Maybe one more thing I wanted to say is that when we compute with this, we discretize our input. So we work with simplicial filtration. So if we're working with this union of balls, maybe we take a check complex or some other construction in order to have a discrete input that we can actually translate into some linear algebra computation on the computer. So if you've heard of this, or if you're familiar with this, then the standard TDA pipeline is very much descriptive. By which I mean the following: that if you look at the kinds of applications or the kinds of problems that people tackle with persistence, the usual setting is the following: you take your data, you build the filtration, you compute persistence diagram, then you build some kind of machine learning or statistics model on top of it, and then you use this to predict the target property. So you can think of persistence in this case as really picking out topological features in some kind of a stable way, and using this as input to a statistical model. Another example of what people do with this kind of idea is they use persistence for detecting stable features and segmenting the domain using those stable features. So we've used this kind of stuff to segment these three-dimensional computational tomography scans of materials. You can use it to do functional connectivity segmentation in the brain regions. That works great. There are other uses. For example, you can use when you find these features, you can use them for dimensionality reduction, meaning you can find maps from your data to simpler spaces. So, for example, the circle in this case. But that's also, again, you're not changing anything about your data. You're just describing some kind of a behavior. And maybe just to make this a little bit more concrete, I'll just give one vignette of this part of the pipeline from our work, just to give to make this concrete if folks haven't seen this before. The application comes from material science. So there are these nanoporous materials called zeolites. They use so they have very complicated channel and pore structure, and they're used industrially for separation of gases, for storage, for delivery. Wikipedia tells me they even used in cat litter, which is kind of a surprise. But they're very interesting in chemistry because they can be used as sieves. So they have different size pores, and different kind of gases can, for example, pass through, and some get stuck because of different pore sizes. And so people have studied them for methane storage, for capturing carbon dioxide, non-separation. And it's possible to take a structure and run a very expensive computer simulation to actually predict these properties, but the simulation is expensive. And so it's natural to want to build a machine learning model in this day and age so that it can predict the properties of these materials without having to run the full-on simulation. And so this is where persistence can be useful. But the way this is done traditionally is that computational chemists derive certain structural features. So if these are your atoms of your crystal structure, these are your pores, then chemists derive features like accessible volume. So what is the volume of the pore space that is accessible to a guest molecule of a certain size, or surface area, or crystal density, or largest cavity diameter. So what is the largest sphere that can fit into the pore space, or pore limiting diameter, which is what is the largest sphere that can pass through the space. But you can, of course, throw any other features that make sense to you. In particular, you can throw persistence diagrams into the picture, and this would be the persistence diagrams of the setting of growing balls, right? So if I take my atoms to be little balls and then I start growing them, I can keep track of how the homology of the space changes. So how the pores get filled in, how cycles get created, how connected components change. And there are other features, so this is just a sketch. So when you compute the persistence diagram, in order to feed it into a machine learning model, you have to take an extra step, because machine learning models, well, at least many of the traditional ones don't work so well with sets, which is what the persistence diagram is, and rather prefer some kind of vectors. So one way to vectorize these diagrams was proposed by Henry Adams and collaborators. And the idea is that you can take a persistence diagram that describes the shape. Okay, you can rotate it just for ease of working with it. Then you can replace each point by a little Gaussian blob with a particular variance sigma. And from this you will get, and then you can also add a weight for technical reasons. And from that you will go from a point set in the plane to really a function. Sorry, when you have this function, then you can discretize it. So you can sort of replace it from a continuous function, just put it on a grid, and you will go from a persistence diagram to this sort of, well, persistence image, but you can really think of it as a vector. And so this is the construction that we use. So the overall pipeline is the following: we take our atom, our material, we grow balls around its atoms. So we compute the persistence diagrams, we turn them into persistence images, and then we train the machine learning model that is a random forest, and we use it to predict, and we train it on a particular property. So our target property is methane adsorption, so how much methane the material can absorb at a given pressure. We predict this property and we measure the error. And we're going to evaluate this across a range of pressures. So for every pressure, you get a certain absorption rate, and you can compare how well your prediction works for different pressures. So that's the pipeline. We use this R-squared score to evaluate it. And so what we get is the following: the baseline are just the features that the chemists engineered, no topology involved. If you use just one-dimensional topology, you actually get something worse. It does not have enough information. So higher is better, I guess, in this picture. And on the horizontal axis is the pressure. So for different pressures, you're evaluating the quality of the prediction. So one-dimensional topology by itself does worse. Two-dimensional topology, which is keeping track of the cavities, which is, I guess, where the gases can accumulate, is starting to perform better at the low pressure. If you combine 1 and 2-dimensional topology. Now you're outperforming the baseline. And finally, if you take everything together, so you take the baseline and the combined topology features together, you get by far the best performance. And so the idea is that persistence captures information that is not captured by these hand-tuned, hand-engineered features that computational chemists were using, and that's somehow, that's clearly beneficial. What's nice also is that these models, so these random forests, they assign an importance to the individual components of the vectors that you feed into them, which in our case translates into assigning importance to both the features that the chemist picked out and the parts of the persistence images that we compute. And what's nice about that is that the parts of the persistence images you can, so for example, if you take, so this is okay, so this is some part of the persistence diagram that's somehow important for predicting the adsorption at 5.8 bar. And you can look at what are the features in your materials that correspond to this kind of to the features in this part of the diagram. So what are the shapes of the cavities in your material? And so this is an example. And this somehow is, well, to I guess chemists, they can make sense of this and interpret why this matters more or less. And similarly, another thing that you can extract out of this is sort of this description of across the different pressures, which parts of the input matter. So is it the baseline features that matter? Is it 2-dimensional topology that matters? Is it the 1-dimensional topology? And so at low pressures, the 2-dimensional topology captures the most information. It's somehow the most discriminative. But when you go to higher pressure, somehow the gases start sticking to the walls, and so the accessible surface area is what matters. And this is what you see here, that the baseline starts dominating. So that's okay, kind of in a 10-minute very quick walkthrough using persistence for a machine learning pipeline. But the point is that this is purely descriptive, right? We took some materials, we took entire database of materials, we computed persistence diagrams, we made some predictions. It tells us something about these materials, but it's all, we can't really manipulate them. But on the other hand, it may be desirable to, okay, so you found that these kinds of features matter for the adsorption, for gas adsorption, such and such pressure. Maybe can we engineer materials that promote those? That's inaccessible, right? And so at this point, I want to transition to this idea of operational topological data analysis. But maybe this is a good time to pause and see if there are questions, because I'm going to move on to a slightly different topic.
I have a question, if you don't mind.
Not at all.
When you were talking about the random forests, you had a holdout set, but what was the out-of-bag score for the training?
Oh, I would have to look this up in the paper.
Oh, I'm sorry. Not a problem.
No, I don't. I mean, this is I don't know, 4 years ago. I don't remember the.
Fair enough. Thank you.
Okay.
Sorry, somewhere it was written that it is hard to use this persistence homology for 3D geometry. What did you mean? What's the problem? Because all the examples I've seen are in 2D, right?
Sorry, I think what I wrote is that it's in general difficult to feed 3-dimensional geometry directly into a machine learning algorithm.
Into machine learning algorithm.
If I give you positions of atoms, it's actually, I mean, it's a very active research area of how to incorporate that into a machine learning algorithm. For persistence, there's no problem. Right?
I see. Thank you. Sorry.
No, not a great question. Okay, so I want to shift gears and talk about what I'm calling operational topological data analysis, and I mean this in the sense of operations research. So trying to optimize or sort of control things using TDA. So this is an idea that's emerged. Well, now over the last 8 years, it really became active over the last, I don't know, 5 years maybe. And the idea is the following: that if you compute persistence, you can use it as to guide optimization. So you can formulate a loss using persistence, and then you can use standard machinery to try to optimize your data or your model or whatever tunable parameters you have, guided by this loss. So the first place this idea popped up was in the work by Gameiero, Hirooka, and Abayashi, where they were trying to interpolate between point clouds by taking a point cloud, taking some target persistence diagram, and trying to move one persistence diagram to another by changing the point cloud. Another example, early example of this came from the work in geometry processing by Polinard, Shkab, and Ovsyannikov, where they take a collection of shapes, they compute persistence diagram of some function that makes sense on the shapes, which is sensitive to sort of the extremities, right? So it's somehow high at the hands and feet, and low on the body. And then if they have two shapes and two meshes, two shapes in two different poses, they can try to interpolate between them by interpolating between this persistence diagram. And the third idea that I find especially sort of appealing is using persistence as a regularizer in machine learning. So the idea is the following: when you train a machine learning model, it often overfits to your data. And the way that this overfitting manifests itself is that the decision boundary, so here's a figure from their paper, there's blue points and orange points. The decision boundary can become noisy, namely it has lots of topological features because it's trying to sort of learn that there's a orange outlier in the middle of a blue point cloud. So you need to classify points in that region as orange, but this is an artifact of noise. It's not really something that you actually want. And so this is Chao Chen and co-authors. They suggested this idea that if you regularize your machine learning training, namely you penalize the complexity, the topological complexity of the decision boundary of your classifier, then you can improve the prediction by reducing the overfitting. And I think that's a very powerful idea that I think people are looking into more. And finally, another thing that this connects to that I'll come back to is persistent simplification. So maybe let me dive a little bit into what I mean by using persistence as a loss. So suppose that we have a persistence diagram, and we can define a loss by prescribing where the points should move. So for example, if I have a persistence diagram, I can say that I want to get rid of all of these noisy points by saying that my loss is going to be the sum of the persistences squared for over all the points in this pink region. So for all the points whose persistence is less than epsilon. Right? If you minimize such a function, well, the best way, the only way to minimize it is to push all of these noisy points into the diagonal, which would get rid of the noise, right? So if you remember my Everest example, all the little bumps on Everest, they're all the points close to the diagonal. And so if you try to minimize the sum of their squared persistences, then this will naturally try to simplify the function. Another example of what you might want to simplify is you might want to get rid of all the points in a particular quadrant. Because what are the points in the quadrant? Well, these are the points that were born before, let's say, time 0 here, and that die after time 0. Well, that's exactly the points that are either in the sublevel set or in the level set, depending how you define your setup of the function. And so if you want, for example, this regularizer to simplify the decision boundary, if you want to minimize the topological complexity of a particular, let's say, sublevel set, well, you can just say that the points in this quadrant need to move out of the quadrant. In other words, our loss is going to be the maximum of the distance to the nearest boundary of this quadrant. And this is, so that's what I said, that this idea is useful for reducing overfitting. So this problem has some history, the problem of persistent simplification. So it can be formulated as follows. So suppose that we have a function f, and we're given some threshold epsilon. Can we find a function g such that it's epsilon close to f, such that all the points within epsilon are gone? So if I have, this is my function f, I give some threshold epsilon, and I want to find this function g such that it irons out these wrinkles so that the points within epsilon are gone. So this problem is almost 20 years old now as I'm formulating it. We know how to do this in linear time very efficiently for extrema, for piecewise linear functions. So these are the three relevant citations, but only for extrema. And if you want to do this in middle dimensions, so for example, if you have a function on a 3 manifold and you want to simplify, pairs between index 1 and index 2 critical points, it's actually very challenging. And the reason it's not difficult to see why it's challenging, because the domain comes into play in a very sort of fundamental way. So if you take a function on a homology sphere, then what will its persistence diagram look like? Well, there's going to be a homology 3 sphere. There's going to be a point in 0 dimensions corresponding to H naught being to there being one connected component, a point at infinity. There's going to be a point at infinity in the three-dimensional diagram corresponding to the homology of the sphere. And then there's going to be a whole bunch of points with finite persistence. If I pick my epsilon to be higher than any one of these finite points, then suppose that I could simplify this function. Well, if I could simplify this function, then I would be left with a function with just two critical points, the one that generates this point and the one that generates this point. Of course, if I had a function with just two critical points, then my domain has to be, honest to goodness, three-sphere, not the homology sphere. And so that's a contradiction. And so whatever procedure that one can come up with for solving this problem inevitably has to take homotopy into account. And so the problem is quite challenging, but it's very important applications. I mean, the desire to simplify functions on three spheres is more than 20 years old at this point. Okay, so let's talk about optimization, unless no, I don't see any question. Let's talk about optimization. So I said you can formulate a loss. You can formulate a loss in terms of persistence diagrams, and so this loss you can translate as just gradients on individual points. So how any particular point in the persistence diagram needs to move. Now, when we compute persistence on real data, we always work, I said, with simplicial filtrations, and so I can think of a filtration as a function on the simplicial complex, and so each point in the persistence diagram, its birth and death values come from a specific simplex, right? So a homology class is born when we add the simplex, and a homology class dies when we add. So it's born when we add sigma, and it dies when we add tau. And so if you want to move this point f sigma f tau by some gradient GP that comes to you from your loss, well, this really translates into you have to change the value of f sigma and you have to change the value of tau. Now, depending on what your f is, now that's a particular construction, you can now backpropagate this information and try to change the actual input data. The trouble is that it's not nearly as simple as it sounds, and it's easier to see why this is not as simple as it sounds if we just look at an example. So suppose that we have this function. So this is a function on a graph, on a path, and it's just a height function. I'm going to have a persistence pair between this function value and this function value, which is really translates to the component created here is going to be killed by one of the edges that is added together with this vertex. The persistence diagram is on the right. There is a point here, and then there is a blue point here. And suppose that my loss is such that I'm trying to push this blue point towards the diagonal. Well, if I backpropagate this information to here, this will just translate into let's push this point up and this point down. So we can take a step with that. But as we take a step with that, we introduced a new wrinkle, and our persistence pairing that's responsible for this point that we were moving has changed. So it moved from this point and this point to this point and this point, and now there is this little extra wrinkle, which is an extra point that came out. Well, we can try to push these points down. We'll take a step. The sort of the optimization recovered itself. The function is now okay. So we can take another step, and now we have a whole bunch of these wrinkles reintroduced. So the problem is that it's a highly nonlinear problem, and as we're walking around the space by performing this optimization directly, we're changing the function in a way where new topological features are created, new points appear in the persistence diagram, and getting this to work on real data is actually quite challenging because it's a complicated non-convex problem. There have been other algorithms, more sophisticated algorithms proposed. So one particularly interesting algorithm was proposed by Lejeune, Carrière, Lacombe, and Steve Udo. And the idea is roughly the following: that if you take the domain of your filtration, you can think of it as really a function on Rn, where n is the number of simplices, but the domain is stratified by the permutations of simplices. Because when you compute persistence, the only thing that matters is the order in which the simplices appear. The specific function value will affect the persistence diagram, but the pairing of the simplices, so which simplex creates a class and which doesn't, because the filtration itself won't change. And so if what we saw in the previous slide, the most naive gradient descent, it bounces between these strata, right? So as we started here, we take a step, now we're in a different stratum, different pairings, so we have to go in a different direction. And we keep bouncing, and this wastes a lot of time. And so what they suggested is this idea that you can, at any given point, you can sample the gradient from the nearby strata. And how to do this is a interesting technical problem. But if you sample this gradient, you can identify the steepest descent direction in the subgradient and follow that, so that you avoid this bouncing problem. And it's an interesting idea. It's a non-trivial idea, but it's still, I mean, in practice, it's not nearly as simple as a kind of convex optimization or something like that. So what I want to do in this talk is I want to kind of open up the persistence black box and try to understand the structure of this problem and try to figure out if there is a better solution, so more efficient, more robust way to perform this optimization. Now, it's hopeless to do in general. The problem is very hard. And so I want to restrict my attention to a special class of problems. And to define the special class, I want to observe that most of the losses that people formulate, they can be phrased as a partial matching between the points in the persistence diagram. So I have my blue persistence diagram, I have my target red persistence diagram, and really I can think of this loss as I'm trying to move points, the matched points, the blue points to their matched red points. So just as an example, right, when I talked about this epsilon simplification, where I said that my loss is let some persistences squared of all points whose persistence is less than epsilon, well, I can think of it as that I matched all the points whose persistence is less than epsilon to the nearest point on the diagonal, and now I'm just trying to move using this formulation these points over there. If I'm trying to move points out of the quadrant, well, again, I can match the blue points to the nearest red points on the boundary of the quadrant, and again, this is my optimization problem. So what I want to do is I want to restrict my attention to the simplest possible setting, namely where my partial matching consists of just one pair of points. I have a blue point P, I have a red point Q, and that's it. So in particular, this optimization is completely oblivious to what happens to the rest of the blue points. It only cares about how this blue point moves to the red point. Okay, and so I want to understand exactly what happens in this case. But before I go, I should take a pause and see if there are questions. There are no questions. Okay, then I will keep going. Okay, so I said that I want to open the persistence black box, and so now is the time for that. The way that persistence is computed in the algorithms for computing persistence, they work roughly as follows. We take our simplicial complex K, on which the function f is defined. We take its boundary matrix, call it D, so this is going to be my boundary matrix, and we order the columns and rows by this function f. And then we perform column operations on D from left to right to bring it into this reduced form. And the reduced form is such that, by definition, it's when the pivots, the lowest non-zeros in any given column, is in a unique row. And so you can imagine, sort of, this is the greedy algorithm that does this, where if you have two pivots in the same row, then you use the one to the left to get rid of the one to the right, and that's essentially what this algorithm is. And you can think of this computation as a decomposition. So you compute the decomposition of R as this product dV. And so I want to interpret this a little bit. So what I said is, so here suppose is our function. Imagine that the entire domain is triangulated, and now we have a persistence pair sigma. So a cycle created by the addition of edge sigma is going to be killed by the addition of edge tau. Well, in this matrix, this will manifest that the pivot in the column of tau falls in the row sigma. But there is more in this in this computation, namely the column of tau itself is actually a cycle, right? It's a sum of a bunch of boundaries, so it's exactly the this blue cycle that I'm showing in this figure that is created by the addition of sigma. So that we can recover immediately from the column of tau. But what's more interesting is actually the column of tau in matrix V, because okay, so it's a chain whose boundary is the cycle tau. So it's exactly this red cap that is added when we add tau whose boundary is sigma. So the reason you can really think of it as a certificate. This column certifies that the cycle created by sigma is killed by the addition of tau, because the boundary of this chain is exactly this blue cycle. And this figure is suggestive, and it's suggestive. It hints that, well, if I wanted to cancel this pair sigma tau, right, what I really have to do is, it's not enough to just push tau down to sigma. I actually have to move this entire cap down, because in order for me to cancel this pair, I really have to, I basically have to flatten this cap. I have to bring everything in red to the level of sigma. And well, one should be suspicious of these kinds of figures, but in reality, it turns out that this figure captures the situation completely. That if you want to perform this kind of optimization, this is what you have to do in all settings. Okay, so what I want to think through is what happens if we were to perform this procedure. So if we start pushing these simplices down as we perform this optimization. Well, I want to think of the filtration as just the ordering of simplices. I have my simplex sigma that created the cycle. I have my simplex tau that destroyed the cycle. And now suppose that I want to decrease, I want to cancel this pair by moving tau towards sigma. Well, if I start performing this, what I have to understand is what happens if I transpose tau with the simplex that immediately precedes it. Because one of the two things can happen. Either the pairing changes, and when I move tau to before tau 1, now tau 1 becomes paired with sigma, or it doesn't. If the pairing changes, then I say that tau 1 has to enter this critical set. So it's going to be a simplex that's going to be paired with sigma if it comes last in the sequence. If it doesn't, then I can forget about tau 1 because it's not doing anything. And now I can just rinse and repeat. I can keep moving this entire sequence of simplices in the critical set. I can check what happens to the simplex that precedes it. If when I move it to the right, it becomes paired with sigma, then I have to add it to the critical set and move this entire thing together. If it doesn't, then I can forget about it. And so this crucial object that I care about is what I call a critical set, which is this contiguous sequence of simplices, such that if I place any one of them as, well, in this case, the last one, it's going to become paired with my reference simplex sigma. And it's the same definition for birth, death, increasing, decreasing. It's just this contiguous set of simplices. And it's helpful to understand what this critical set is if we think about the optimization in this filtration space. So if I take this space, this Rn, where every filtration is a point in the space, and the values are just the values that are on the simplices. So imagine that I start with this sequence. So I have my tau 1 is equal to 0, tau 2 is equal to a quarter, tau 3 is equal to 3/4. So it's a point here, 0, a quarter, 3/4. And my goal, and I imagine that tau 1 is paired with some sigma, and my goal is to move tau 1 from value 0 to value 1, right? So to the right hand side. Well, I can start this process, I can start pushing it, but when the value of tau 1 becomes the same as tau 2, in other words, when we reach the diagonal here, I have to check what happens if I go to the right. In other words, when the order switches. If nothing happens, then I can keep moving. But if, for example, now I reach the tau 3, and if I switch the order, tau 3 becomes paired with it, well, then I actually have to keep moving along this diagonal. I cannot keep going to the right, because now the gradient will be given to me by tau 3. It will push me up to the side from here, and really on this stratum, it's going to follow the diagonal. And so if I can identify this critical set, then it tells me lots of interesting things. It tells me what is this final stratum on which I'm going to be moving, but it also tells me what is this final point that I'm going to be moving to, because it's exactly the simplices in the critical set that get the target value. So the target value for tau 1 was 1, and it's exactly tau 1 and tau 3 that get this value. So if I can identify this critical set somehow a priori, then I don't have to follow this gradient flow. I don't have to simulate anything. I can just go directly from my origin to my destination, and I will call this big step once I identify the critical set. And maybe one more illustration for why things behave this way is that if I restrict myself to the plane that's defined by simplex tau 1 and tau 2, which tau 1 is in the critical set, tau 2 is not, then the gradient of my optimization simply follows from left to right. It doesn't care, but it's independent of tau 2. But if I am on this plane, tau 1, tau 3, where both tau 1 and tau 3 are in the critical set, well, then the gradient restricted to that plane, if I'm above the diagonal, it's pushing me to the right. If I'm below, it's pushing me up. And along the diagonal, it wants me to follow the diagonal. So that's kind of the key structure of this problem that follows from the existence of this critical set. Now, I haven't told you. I mean, there's a bunch of details I'm skipping. I mean, you have to make sure that the critical set is well defined. That there are lots of other details I need to check. This all essentially follows from the fact that if I have to synthesis sigma and tau, their pairing, whether they're paired, depends on what comes between them and before them, but it doesn't depend on the order of simplices that come between them. So that's somehow the crucial reason for everything. And so once I sort of check these facts, and once I know that critical set is well defined and it exists, I can immediately define an algorithm which I sort of have been implicitly following all along that just simulates the gradient flow combinatorially. I start moving my simplices, I try to swap them, and then check if the pairing switches or not. If the pairing switches, I start moving them together. If it doesn't, the simplex doesn't belong to the critical set, and I can skip it. So that's kind of a naive algorithm, and it runs in a cubic time. So it's m squared n, where m is the number of simplices between my origin and my destination, and n is the total size of the simplicial complex. So the main result of sort of the paper that this presentation is based on is that it's possible to identify the critical set in linear time. And the idea is that, so when I said that we can compute, we can think of persistence computation as this matrix decomposition, so sort of this reduction, where I take my boundary matrix D, and then I reduce it, but I keep track of the operations in matrix V. U is the inverse of V, where I can also keep track of these operations, and then I can think of D as a RU decomposition. Then what happens is the following. If I'm trying to increase the value of some depth simplex tau from D to D prime, it suffices for me to find the row of tau in matrix U and take all the non-zeros in this range, D to D prime. That is going to be exactly the critical set. And if I'm trying to decrease that, then this was the illustration that I showed you earlier, where there was this cap, and the cap was exactly, the chain representing the cap was stored exactly in the column of tau. So it suffices for me to take the column of tau in matrix V, look at the range D to D prime, and take all the non-zeros in this range. And that's going to be exactly the critical set. So if I've computed persistence and I have this decomposition, then I can compute this critical set in linear time, just read it off from the column. So that's somehow the main result that, well, I won't prove, but it's in the paper. Questions? No questions. Okay. So this result is, I said this, that if I want to increase depth or I want to decrease depth, the result is about depth. So if I want to move point vertically, I need to also be able to move the point horizontally. But thankfully, there is a very simple trick. And the very simple trick is that we can switch from homology to cohomology. So we're working on field coefficients. If we switch from homology to cohomology, we'll get exactly the same persistence pairing. So if a class is born at Ki in homology that dies at Kj, then the class is going to be born as we leave Kj in cohomology, and it will die at Ki. Computationally, if you want to compute not persistent homology but persistent cohomology, you need to simply change your matrix. It's take an anti-transpose. So I will take a transpose of my matrix D, but I will also reorder the order to go not from 1 to n, but from n to 1. And now, if I compute the persistence decomposition, well, I'll get the same pairing. So if sigma is a pivot in the column of tau here, then tau is going to be a pivot in the column of sigma here. But otherwise, everything stays the same. And namely, the exact same reasoning that told me that I can use to prove that in order for me to increase or decrease the value of the depth, well, now the role of death, namely the column in R, is taken on by what is actually birth in the homology order. And so instead of looking at matrices that come from the decomposition of the boundary matrix, I can look at the matrices V, perp, and U perp that come from the decomposition of this transposed matrix D. And so all of this can be summarized in a set of rules to where if I want to increase birth, I have to look at V perpendicular, decrease birth U perpendicular, increase depth U, decrease depth V, and then there are some special things that happen for points at infinity. But the point is that it's a very simple set of rules. And if you simply compute this decomposition, which we're already computing, you don't have to now work with either taking gradient flow or doing the sort of this kind of gradient descent where you take these little steps. You can just identify the critical set and you can take a big step all at once. Now, there are a few more details that I haven't said too much about. Namely, in all of this, we have to make sure that at any point in time, we have a filtration, namely that the faces come before the cofaces. So this is somehow important to have all of this well defined. And so if we actually were to do this carefully, if we were to figure out what the critical set is, we also have to make sure that when we're decreasing when we're moving a simplex to the left, we have to move all the faces of the simplexes in the critical set together with it. And if we're moving to the right, we have to make sure that we're moving all the cofaces. So technically, that's something we have to worry about. But in reality, we can ignore this in practice because what will actually happen is that when we identify the critical set and it gives us a gradient and we backpropagate it to the actual data. So for example, we're moving points in the point cloud or we're changing the values of the function. Well, then we have to, once we take a step and we make an update, we have to recompute the function because it's still going to be an optimization iterative process. And when we recompute any one of these constructions, it will automatically guarantee to you, it will ensure that by construction, the faces will come before the cofaces, so you will always have a filtration. So it's something to worry about in theory, but not in practice. Okay. So now let's summarize all this because what I showed is what these critical sets are and how to identify them for a singleton loss. So if I'm trying to move just a single point, but of course, in real problems, you care about the entire matching, right? So you have a bunch of points that you want to move around all at once. And so the question is, what do you do in this setting? And so our algorithm is the following. So we'll go through all the points, through all the pairs in the matching. We will identify the critical sets for births and deaths for each one of these points. And for every simplex in the critical set of the birth and the critical set of the death, we will accumulate the target values that the critical set wants it to go to. So there will be any given simplex can belong to multiple critical sets, and so it will accumulate a whole bunch of these target values. And so now we have to decide where to move any given simplex, and we use a simple heuristic where the target value that is the farthest, that's the one that's going to win. So whichever critical set wants to push our function our value the farthest, that's what we're going to do. And the rationale for this comes from the following. So suppose that I have a function and I want to push all of these points into the diagonal. So I want to minimize points whose persistence is I want to simplify points whose persistence is less than something. Well, if I take this point, its critical set is going to be this entire blue and purple mountain. So this entire thing. If I take this point, its critical set is going to be this little purple range. If I want to simplify all of this, so the purple this point will tell us to move this purple critical set down to this saddle. So just squash this to get rid of this. This point will tell us to move all of this down to this saddle. And of course, in this case, what you really want is to get rid of everything at once, and so it makes sense to push everything down to the saddle. So it's a heuristic. We've tried other heuristics, for example, using averaging of the target values. It all works basically the same. So a few results from a few experiments. So we took some data set that's used in scientific visualization. We took its persistence diagram and we tried to get rid of the points in the quadrant. So I should maybe explain. So I took the persistence diagram and I rotated it by 45 degrees. So now the persistence, the distance from the diagonal, is on the vertical axis. The diagonal itself is the horizontal axis. And my objective is to push the points out of this quadrant. What I'm showing is, and on the right is the optimization step versus the persistence of the points plotted on the vertical axis. And what I'm showing is all the optimization steps laid over each other, where the color is showing to us where we are in this optimization. So what you can see here is that the fact that the points start out and you see yellow points inside the quadrant, it means that they're not reaching the boundary of the quadrant. And this I should say this is the traditional optimization. So this is the standard optimization method, which we call diagram method, which just does gradient descent locally on the simplices that are responsible for these points. If we switch to our critical set method, which now pushes entire ranges of points, well, what you can see is that these points, all of them, the yellow points are all on the boundary. They all reach the boundary very quickly. And it's even easier to see if we look at the loss. So if we look at how this loss behaves during the steps of this optimization, well, the top three curves is the diagram method. So the standard optimization, the loss is decaying slowly, although momentum here helps a lot. And the critical set method are these three curves, and you can see that it very rapidly figures out what needs to move where, and it's very rapidly optimizing the function. Another experiment is with resistance simplification. So this is exactly where I was saying that I want to push all the points into the diagram. And we're working with one-dimensional persistence. So it's exactly the difficult case which we don't know how to solve. So this is a pairing between index 1 and index 2 critical points, not the extrema. So this is the diagram method again. Its goal is to push all the points into the diagonal, but the fact that you see this yellow blob here means that not all of them have reached the diagonal in 50 steps. If you use the critical set method, well, all the yellow is on the diagonal, everything got squashed, and you can see in this profile plot that the persistence decays very rapidly. And the same story if you look at the loss function. This is on the logarithmic scale, right? And so the critical set decays significantly faster than the diagram loss. One more thing that if you work with optimization, you know that one problem that's a sort of a perennial problem is that there are lots of hyperparameters to tune. So if you're doing gradient descent, you have to decide on how big of a step you're taking. And so what this plot shows is how many steps you have to take to reach some prescribed loss value. And the point is that the critical set method does this a lot better, and it's a lot less sensitive to the hyperparameter tuning, namely the learning rate. So in the best case scenario for this problem, it requires 10 times fewer steps, but it decays as you increase the learning rate, which is very desirable. And then finally, there is some sort of data to show that the critical set gets faster as our data sets get faster. Okay, I think this is what I wanted to say. I want to conclude this by sort of summarizing. I think this persistence guided optimization offers a brand new class of applications. It's very exciting. There are new ways to use topological data analysis, what I call the operational topological data analysis. Besides machine learning, I think this will be very interesting in shape optimization. So, for example, to try to modify materials to promote certain kinds of pores and cavities. By opening the persistence black box, you can identify these critical sets and develop much faster, more robust, efficient algorithms. But I think there's a lot more work to do. There is the interaction of this algorithm with various filtrations is a wide open problem and a very interesting problem. And I think this also offers some new insights for descriptive TDA. Namely, you can construct distances between the diagrams that are take more of the structure into account, but that's a topic for a separate talk. So at this point, I want to stop. I want to thank all of you for your time and attention, and the paper is on archive and the code is on GitHub.
Thank you. Very nice for this lecture. So do we have any further questions for Dmitry? Just unmute yourself.
I have a question.
Please.
Hi, Dmitry. Thanks for the nice talk, as usual. One question I have is like, there is this whole field of topology optimization. like, do you know how what you do compares to what those guys do there? Like, I don't know what they do, but maybe you know.
So my understanding is that they solve a very different problem, right? So they're trying to optimize the topology of the meshes or the placement of certain points for some objective that they have, and it's kind of much more local questions, right? So where is the front of the wing of an airplane where you really want to run your PDs, rather than this is very much about homology and global connectivity, which, as far as I know, they don't touch, but I'm in no sense an expert in that area.
Okay. Maybe one more quick question. The last data sets, you said they were downsampled to like 32 cubed. Was it like cubical data? Or
the data was cubical, that's right. I mean, there were also experiments with larger data sets where we perform faster, yeah. But the actual vineyards or whatever I was showing were for 32 cube, yeah. It's just a function on the grid.
Sure. But do you compute it as a cubical complex, or is it as something else?
No. We almost certainly work with simplicial complexes, so it's probably Freudenthal triangulation, and but I mean, all of this. So I guess everything applies to cubical complexes, just because everything I said is about this RDV decomposition, which just any cells that.
Yeah, I'm just curious if you can speed it up by like doing some of the usual, like, discrete Morse theory tricks, which tend to help a lot for cubical filtrations. And like in a sense, I think what you're computing is kind of very similar to computing the discrete Morse complex, but
that's right. So it would be very interesting to understand the relationship between the critical sets, for example, these columns of V, and the discrete Morse complex. Because you're absolutely right that some of it's one-to-one, right? I mean, this V is exactly what you do, all of these tricks that you're describing, it's really finding out what, sort of compressing V down to a single cell, right? On the other hand, when you're going the other direction, when you're trying to increase the critical set that comes from matrix U, I do not know what the relationship is to discrete Morse theory, or if there is any relationship. It's really it's really capturing something else, and I would love to understand this better, but apparently I don't. That's a great question.
I had a question. This is really interesting, and I was wondering, one of the things that I guess a lot of people have been thinking about is this idea of like generative modeling, right? And so, say for example, I have a material like the zeolites where the persistence homology is really the most important feature of the system. Do you think it would be possible to create a sort of generative model where it takes in, the actual structure of the zeolite, but the loss function in the autoencoder, let's say it's an autoencoder, the loss function is purely determined by the difference in the persistence diagram. And so what you could do is you could generate materials that have the same persistence diagram, but different, potentially different structures. And then that latent space, you could construct new materials that have similar persistence homology, but, they could be wildly different, molecular positionings. And I think that'd be really important, especially for like amorphous materials, where the positioning of the particles doesn't really matter much. It's more about the topology of the system that really matters.
Yeah, that's a fascinating idea. So I've thought a little bit of what I mentioned, to where if you have a given material, or you have some point set and you want to modify it towards some target, but what you're describing, to where you build a generative model where the loss is explicitly to bring the diagrams close together, I have not thought about, but it's a fantastic idea. Yeah, very interesting idea.
Yeah, I'd love to talk to you more about that offline.
We should talk offline. Yeah.
Yeah, awesome. Thank you.
Good. Do you have any more questions? Okay, if not, we thank you very much again.
Thanks a lot.